Okay, thank you for the introduction. Hi, everyone. I'm Tan Van Vu from Kyoto University. So first, I would like to thank the organizer for giving me this opportunity to present our study in this very nice workshop. And today I'm going to talk about a recent study on the relationship between thermodynamics and the fidelity of quantum gate. So this book was in collaboration with Tomotaka Guara at Deakin and Keizi Saito at Kyoto University. And the detail of the talk can be found in this archive paper. So this is outline of my talk. So I will start with a brief background on quantum gate and the motivation of our study. And then I will explain the setup and our main results with a simple numerical demonstration. So in the last 2 decades, we have seen a significant progress in the development of quantum computing, which has been experimentally realized in various platforms, including superconducting qubit, trapped ions, a photonic system, and nuclear magnetic resonance. And in general, quantum computing process is carried out by applying a sequence of quantum gate, and each quantum gate acts locally on multiple qubits. And it's obvious that the accuracy of quantum computation strongly depend on the fidelity of quantum gate. So that's why achieving a fast and high fidelity quantum gate is crucial for reliable quantum computing. And in recent years, there are many experimental proposals with the aim of building high performance quantum gate. As shown in the reference, there are many experiments with trapped ion and superconducting qubit, single qubit, and 2-qubit gate. And ideally, we expect that the quantum gate is a closed system where coherent control can be applied, and the dynamic is given, the time evolution is given by a unitary operator like this. However, in reality, the quantum gate cannot be perfectly isolated from environment, and which mean that just the quantum gate is no longer a closed system, but an open quantum system. And the unavoidable interaction between the quantum gate and environment lead to the quantum decoherence. And as a consequence, the fidelity of quantum gate also degrade. And so we can see that the quantum gates are unavoidably affected by noise, which come from various sources, like including thermal fluctuation, crosstalk between qubits, or even from external control. So till now, several studies have analyzed the gate fidelity under some specific situation. For example, in the presence of conservative law for short operational time, imperfect time picking, and even for fluctuating external control. Now, however, the impact of environment on the gate fidelity from perspective of thermodynamics remain poorly understood, and this leads to our motivation to elucidate the thermodynamic effect on the fidelity of quantum gate. We expect that developing a thermodynamic framework for fidelity of quantum gate will not only provide a new way to analyze gate fidelity, but also provide some new insight into the thermodynamic cost of quantum computing. So let me explain our setup. So we consider quantum gate which act on n qubit for simplicity, but generalization to the qubit system is straightforward. So the ideal dynamic without noise is given by a unitary operator UG like this, and the underlying Hamiltonian ST can be derived by some time-dependent protocol. However, the dynamic in duality is not unitary, and the time evolution of density matrix is given by a CPTP map like this. And here we assume that the quantum gate is quickly coupled to the environment. And the time evolution of the density matrix is described by the Dirichlet equation like this. So in addition to this unitary part, we here have several dissipator. We characterize a noise channel, and each noise channel is governed by a Zoom operator LC. And we consider two types of Zoom operator. The first one is dissipative one, so which caused by the energy exchange with the environment. For example, it can be the energy regulation or excitation between the ground state and excited state. And this kind of Zoom operator contribute to the change in the entropy in the environment. So to guarantee the thermodynamic consistency of this quantum gate, we assume the local detail balance. That is, the Zoom operator come in pair LC and LC prime, which satisfies this relation. And here SC is environmental entropy change due to the Zoom LC. And the second one is non-dissipative Zoom operator. So this includes phase damping, which causes a lot of quantum information without energy loss. So for this kind of Zoom operator, we assume that they are Hermitian. So actually, this condition can be included into this local detail balance by setting the entropy chain SC to be 0 and C prime equal to C. So for this dynamic, we introduce two relevant quantities, fidelity and dissipation. So as I explained in the setup, for each input state var5, we have two output state, the one of the ideal dynamic and the other of the geodynamics. So the output state are given in this form. So to evaluate the accuracy of quantum gate, we can look at the difference between the quantum state. And this can be done by calculating the fidelity between quantum state. And because the output state of the ideal dynamic is pure state, so the fidelity become an inner product between the state. So it can be calculated like this. And by taking ensemble average of this fidelity over all initial pure state, we can define the fidelity for quantum gate like this. So actually, this quantity is always non-negative, and it's smaller than 1, smaller than or equal to 1. And for the dissipation, we consider the entropy reduction, which is a central quantity in stochastic and quantum thermodynamics. And entropy reduction for each initial state can be defined as the sum of the entropy reduction of the system and of the environment like this. And the system entropy reduction is quantified by von Neumann entropy, and the entropy reduction for environment can be calculated by taking the sum of the product between the Zoom frequency and the entropy change due to the Zoom, and taking the time integration from 0 to tau. And similar to the fidelity, we can take the ensemble average over all initial pure state to define the quantification for dissipation like this. So this always non-negative, which is nothing but the second law of thermodynamics. So for this quantification of fidelity and dissipation, we obtain several results that clarify the relationship between the two quantities. So the first one is relation between the fidelity and the average entropy reduction. It states that the sum of fidelity and the square root of entropy reduction term is always larger than or equal to 1. And this means that this inequality tells to what extent dissipation can affect the fidelity of quantum gate. And here gamma is a quantity that can be determined using only a sum operator, and is defined in this form. And D here is the inverse space dimension. And of course, this quantity is always non-negative. So as shown in this figure, if we plot it by relation in two-dimensional plane, we can see that there are inaccessible region where dissipation and fidelity cannot be achieved at the same time. And actually, this relation hold true for arbitrary time and protocol, and it can also be interpreted as a thermodynamic upper bound on the error of quantum gate, like this. So this provides a quantification on the fact that reducing dissipation can lead to an improvement of the accuracy of quantum gate. And I have several to remark on these results. The first is why this relation is a thermodynamic constant of fidelity. It can be derived as a low bound on the introduction in terms of fidelity and the quantity gamma, like this. So this can provide a way to estimate introduction from some quantities that can be experimentally accessible. So to demonstrate it, let me consider an example with Pauli noise. So Pauli noise, they are a correlated noise given in the form of the product of Pauli matrix, like this. And here we include the noise with the trivial noise with identity sum operator. So all sum operator have a zero trace. And for the short operation time, we can actually calculate the fidelity and the quantity gamma explicitly using the sum rate like this. And if we insert in the expression to this inequality, we can obtain a simple low bound for entropy reduction. We can be used to estimate the order of the entropy reduction. And actually, this dephasing rate gamma can be estimated from the experimental data as shown in this reference. And the second remark is that this relation can be generalized in more general setting. That is, so far we assume that the Hamiltonian HT is perfectly implemented. But in practice, there may exist some systematic error when we design and controlling this Hamiltonian due to the limitation of control. So the realistic Hamiltonian can be different from the ideal one. So which I denote by HT hat. And even for this setting, we can obtain a further generalization of this relation like this. So now this low bound the low bound one is replaced by this quantity, which in terms of inner product between the ideal unitary and the real unitary. And actually, this low bound is always smaller than 1. However, if we can perfectly implement the Hamiltonian, so this Hamiltonian becomes the ideal one. So the trace equity, and this relation immediately recover the original relation. And the private results apply to arbitrary time-dependent driving. And now we focus on time-independent protocol. So that means that the Hamiltonian H is time-independent, and the sum operator account for some between energy eigenstate. That means the commutator between Hamiltonian and sum operator is proportional to sum operator. And here omega k is energy chain associated with some LK. And for this quantum gate, for this kind of quantum gate, you obtain a more compact and universal relation we state that the product of fidelity and exponential introduction is always larger than or equal to 1. And if we plot it in the two-dimensional plane, we obtain this kind of region which we cannot be accepted. And again, this holds true for arbitrary term. And we can also write a thermodynamic upper bound on the error like this. And interestingly, it can provide a more simple estimation for this patient because here there are no quantities that involve resemble operators. That's only fidelity and introduction. So we can estimate this patient through the fidelity, which can be experimentally accessed from the data. And so far, I explained two results with Markovian dynamics. So now I go to the case that beyond the Markovian environment. That I consider a quantum gate that coupled to arbitrary reservoir, and the coupling can be very strong. And the quantum gate and the reservoir initial time was in product state. There is no correlation. And the composite system undergo a unitary operator, a unitary transform. And finally, there's some correlation between the quantum gate and reservoir. And mathematically, we can write down the CPTP map for this process like this. And here, rho E is initial state of reservoir, which can be arbitrary state. We do not assume that rho E should be Gibbs state or some other state, but it can be arbitrary state here. And here for simplicity, we consider time-independent system Hamiltonian. So this means that the total Hamiltonian is sum of the system Hamiltonian, interaction Hamiltonian, and the reservoir Hamiltonian. And yeah, the system Hamiltonian is time-independent, but the interaction can be time-dependent. Yes. But actually, our result can be generalized to the time-dependent case, but here for simplicity, I only consider the time-independent system. And for this case, instead of entropy reduction, we consider energy dissipation. That is, we take the ensemble rate over energy change. And actually, this quantity reduced to the heat dissipation to the environment when the unitary U conserve total energy. So this means that the unitary U commute with the sum of system Hamiltonian and environment Hamiltonian. So this Q is exactly the heat dissipation to environment. But in general, this quantity should be interpreted as energy dissipation. And for this kind of setting, we obtain a fidelity dissipation trade-off relation. That is, the sum of fidelity and the energy dissipation is always smaller than or equal to 1. And here kappa is defined in terms of Hilbert space dimension and the energy gap energy bandwidth of the system Hamiltonian. And again, we can have an illustration for the fidelity and energy dissipation like this. And again, this holds true for arbitrary time and iteration. The iteration can be arbitrary time dependent. And now this can provide a thermodynamic lower bound on the error. So previous two results provide some kind of upper bound on the error, but now we have some kind of lower bound on the error like this. So this means that we have to suppress energy change in the system to ensure that to guarantee the accuracy of the quantum gate. So let me demonstrate our result with two examples. So we first consider a single qubit quantum gate, which is theta. Theta means that we perform some rotation around the x-axis. like this. And we consider the superconducting qubit with this time-dependent Hamiltonian, and we consider two dissipative sum operator, which account for the energy relaxation and excitation. And we also consider a phase damping sum operator. When we plot this sum of fidelity and dissipation, and we can see that the bound is high, but it can be saturated in the short time limit. But for the long term, the fidelity decrease, but the increase of the dissipation is more dominant. So this sum is more larger than 1. And the second case, second example is a 2-qubit gate, which is a control Z gate. So we consider time-independent Hamiltonian with 4 sum operator. The first two one as a dissipative one, and the last two one as non-dissipative. So we can verify 3 relations derived in this case because the Hamiltonian is time-independent. So we can see the bound is always satisfied. So let me summarize the results. We derive 3 relation for the quantum gate. Which provide quantitative characterization for the thermodynamic effect on fidelity, and this can also be used to probe some information on dissipation through the fidelity of quantum gate. And for future work, we can consider the law of thermodynamics in dissipative quantum computation. So in this case, dissipation can be utilized to perform some desired quantum computation. So it would be interesting to clarify the role of thermodynamics in just a computation scheme. And another one is about the thermodynamic quantum correlation to find a relationship between dissipation and the performance of quantum error correction. So I'd like to end my talk here. Thank you for the attention.